Okay, can you see the slides?
Can, Doctor.
Okay. So before we move on, today is what, Thursday, right? Thursday. So tomorrow I'm going to give you your hold on, let me progress. Okay, tomorrow I'm going to give you your assignment 1. Okay, so assignment 1, I'll post it on eLearn, and you'll be given 2 weeks to complete and upload the answers on eLearn as well, right? Use eLearn submission. So I'm going to give you tomorrow. So it's going to be Friday, then it's going to be another 2 Fridays as the due date. Alrighty, so let's move on to generation and recombination today. So as usual, before we continue, let's recap on what we have learned in our previous topic. Okay, so let's go through question number 1. We have an N-type silicon with donor concentration ND equals to 10 to the power of 17 per centimeter cube. So what is the value of N naught and P naught? Assume Ni equals to 1 times 10 to the 10 per centimeter cube. Okay, anyone? N-type silicon, Nd 10 to the power of 17. So what's the value of N naught and P naught? Remember, the N is the density of electrons and P is the density of holes. And not there, not N naught and P naught, not is the condition for thermal equilibrium. Okay, so density of electrons in thermal equilibrium and density of holes in thermal equilibrium as well. Right, anyone? What's the N naught value and P naught value? Anyone? Let me see the list. Raja Saleh. Raja Saleh, any answer? N naught and P naught? Come on. No answer? How about Ifa? Ifa Farzana. Ifa was the N naught and P naught? In this case? Anything? Are you there? Anyone with answers? How about Raihan? Raihan Shamimi. Come on, guys. What's your answers for this? Satu jawapan.
Doktor,
Go ahead.
apa tu boleh kata kalau N naught sama dengan N yang approximate to ND?
Yeah, yes. Your N naught is, in this case, equals to ND, okay? So like I said before, if the question doesn't state anything about the ionization efficiency, so you can just safely assume that N naught is equal to ND, right? So you can just assume that 100% of the dopants are ionized. Okay, so in that case, N naught equals to 10 to the power 17, right? So therefore, what about P naught? So we've got N naught equals to ND. So P naught is?
Apa namanya?
Okay, go ahead.
Guna NI kuasa 2.
Yes,
Yeah.
law of mass action, right?
Yes.
So what do you get?
I kuasa 2 over N naught.
Yes, so?
1000, Doctor.
1000, right? 10 to the 3. Okay, good. So because our Ni squared is 10 to the 20, so you just divide by 10 to the 17, so you're going to get 10 to the 3 or 1000, right? So 1000 per centimeter cube. So very straightforward. Okay, so all you have to know is law of mass action. N times P equals to Ni squared. And Ni is assumed to be 1 times 10 to the 10 per centimeter cube. Okay, good. Let's move on to the second question. What is drift? What is drift? Anyone? How about Nabila? Nurul Nabila? Nabila ada ke? Dah dengar suara yang saya tak pernah dengar ini. Nurul Nabila? Anyone? What is drift? Senyap je semua ni. Farhan. Okay, Farhan, what is drift? Tak ada juga. Semua sunyi sepi je ni. Movement of electrical charges due to an electric field. Yes. Okay, movement of electrical charges. You kena tambah Farhan, due to presence of electric field. Okay, because if there's no electric field, there will not be any drift component. Okay, remember, to have drift, you need to have electric field. To have diffusion, you need to have concentration gradient. Okay, so how do we calculate drift current density? How do we get drift current density? What is the equation you need to use? J equals to sigma E, sigma times E, okay? And sigma is, how do you get the sigma? What do you have to plug in to get sigma? Ada
E
tiga parameter kan?
plus mu PP.
Okay, so you have to N mu E N mu E Q, right? Q N mu E E. Kalau total, then you have to plus another one for whole, right? Q mu P P, right? PP, okay, good. So then what's diffusion? Tadi dah jawab kan? So movement of electrical charges due to concentration gradient. Then how about the calculation for diffusion current density? What do we use to get the current density? Semalam kita discuss kan? Q times QD dN dx, right? QD dN dx and QD dP dx, and the dP dx is negative component, right? Negative QD dP dx and plus QD dN dx, right? So that's total current density, diffusion current density. Right, the last one. What is the purpose of Hall effect? Why do we need to use Hall effect? Kenapa? Nak pakai Hall effect? Syafiqah. Okay. Farhan dah jawab. Distinguish semiconductors. What do you mean, Farhan? Can you elaborate? Distinguish semiconductors. It's too general. What? How do you tell? What are the parameters that we are probing? Okay, Azwani, to know whether it's p-type or n-type. Okay, that's one of the parameters. What else can we know from Hall effect? You can tell whether your semiconductor or your sample is p-type or n-type. What else can you know from your Hall effect measurement? Apa lagi? To measure the majority carrier concentration and mobility. Yes, good. Okay. So to measure the majority carrier concentration, mobility, you can also get the values of resistivity, shear resistance. Okay. Okay, good. So those are the things that you have to know from our previous topic, which is carrier transport phenomena. So these are the G's of the topic. So if you're okay with these contents, then you are pretty much okay with what we've learned in the previous topic. So that's why doing a recap is very important. Okay. Kadang-kadang kita belajar je, as you learn, then you just drifting through the content. But maybe you miss to pick up certain important concepts in that particular topic. So that's why I love to do recap so that you are on your toes every time. Okay. Then only you are okay to move on to the next topic. Kalau tidak, nanti if you accumulate your misunderstanding from the previous topic, and well, you wait till the final minute, and then the moment you go on to the new topic, and you're gonna be given new contents which require understanding of the previous content, then it's gonna be messy. Okay, so that's why clearing up is very important right there and then. Okay, in this topic, generation and recombination, we're going to look into a couple of items, a couple of contents. We're going to start off with thermal equilibrium and steady state conditions. And we're going to look at thermal equilibrium in intrinsic semiconductor, in n-type semiconductor, and also in p-type semiconductor. Okay, so we're going to see how are they different from each other when we dope our semiconductor to p-type and n-type in comparison to intrinsic condition. And we're also going to learn about excess carriers, and that's why item number 1, we need to cover thermal equilibrium first, because you need to know what is your original condition that you begin with, which is under thermal equilibrium. So that's why you need to know the n0 value, the p0 value before we start to add on new carriers. Okay, so when I say it's excess carriers, so that means we are adding new carriers into the system on top of the thermal equilibrium value. So that's why you need to know what's your baseline, what's your reference, before you have the new figures coming into the equation by the excess carriers. And we're going to look into generation and recombination concepts, and carrier injection, where you're going to learn about injecting new carriers into the system or into the semiconductor at low doping level and also at high doping level, and we call it as low carrier injection and high carrier injection levels. And we're gonna look into basic equations of semiconductor device physics, some of the main equations, and key constants and relationship and parallel currents. Okay, so what is thermal equilibrium and steady state? So the content here is more related to the solar cell, but it's also applicable to device physics generally, right? So thermal equilibrium, the temperature or thermal energy, because thermal energy is associated with temperature of the system, for example, solar cell or some other devices, is constant. So temperature or thermal energy is constant with time, and the same for all classes of particles, holes and electrons. So there are no external agents like voltage or light acting on the system. So this is defined as thermal equilibrium. So you have your temperature or thermal energy constant with time. okay? And at the same time, there is no external agents acting on the system. So for example, if you have a silicon wafer that you are given with, for example, you have, say, P naught of 10 to the 16. Okay, you start off P naught 1016 or Na equals 1016, or your P-type wafer having 1016 of hole concentration per centimeter cube. And then you don't have anything acting on the silicon of that, right? So you don't have anything acting. So you don't have voltage applied to the silicon, you don't have light illuminated on the silicon. So in that case, the silicon is said to be in thermal equilibrium condition, okay? Or all the particles in the box or in the silicon system, if you like, have the same temperature or thermal energy as the original condition. So that's TE, or thermal equilibrium. On the other hand, steady state is a more general state where external agents like voltage or light, in this case, can act on the system. So in this case, you can say that your system is the silicon wafer, or it can also be up to the device level. So silica is only up to material level, it's not yet a device. So it can act on the system, but properties of the system, for example, thermal energy, are constant with time. So you are applying the external agents constantly. Okay, you apply tapi the constant condition, right? Constant with time. So macam kalau you apply light, for example, then the light is illuminating constantly on your silicon, for example. So in this case, the thermal energy of the electrons and holes can differ from each other but do not change with time. So they will have a new level of energy, but the energy is constant with time. Okay, so thermal equilibrium is a steady state. Thermal equilibrium is a type of steady state, but not vice versa. Okay, so this one is important. So thermal equilibrium is a form of steady state, but steady state is not a form of thermal equilibrium. So that's what it means. Okay, so thermal equilibrium is a form of steady state, but not vice versa, because for steady state, you have already applied external forces like voltage or light or whatever to the system constantly, right? Constantly. But in the first case, for thermal equilibrium, you don't apply anything at all. So it's just as in the original condition as, say, as you receive it, okay? So that's thermal equilibrium and steady state. So let's recall what we've learned last time about Fermi-Dirac distribution function, density of states, and eventually density of free electrons and free holes, which can be calculated by the given equation. Okay, so sebelum ni the original equation was say Ne equals to Fe times density of state kan? Ne equals to Fe, Fermi-Dirac distribution function, times NCE for electrons. On the other hand, if you want to calculate for holes, PE equals to 1 minus Fe times NVE. So we've covered this in density of states last time. So let's recall the equations for thermally generated N naught and P naught in a pure or intrinsic SC is semiconductor. So in the intrinsic semiconductor, N naught is given by NC times exponential of EF minus EC over KT after you have plugged in all the important parameters into the original equation. Then you will end up with this equation. And for P naught, is going to be given by NV times exponential EV minus EF over KT. Okay, so we have learned last time when we have intrinsic condition. So we label it as P naught and N naught, intrinsic or pure. So we're going to have a Fermi-Dirac distribution function as shown on the left. Okay, right? So that's a Fermi-Dirac distribution function. Remember, if you recall this, it is the condition as t is equals to 0 and t at higher than t0. Okay, T1 last time. And after we integrate in order to calculate the density of free electrons and free holes, so it's going to be given by this, the shaded red region for electrons and shaded blue region for holes, right? In the conduction band and in the valence band respectively. Conduction band and valence band after the calculation, right? So that's how your N0 and P0 looks like. Electrons and holes are in thermal equilibrium condition with the lattice at the same temperature. So notice that we are going to have N0 equals to P0. Okay, N0 equals to P0 in thermal equilibrium condition. So in this case, if you want to use a law of mass action, you can multiply both N0 and P0, which is equal to Ni squared, and that can also be given by this middle equation. Okay, NV exponential negative Eg over KT, and also equals to Ni squared. So that's the product of law of mass action. So that is the condition for thermal equilibrium condition. Yeah. So let's move on to another condition, which is also thermal equilibrium, but in N-type. So we've discussed in thermal in intrinsic silicon. Now let's look at N-type silicon. So for doped semiconductors like N-type, N0 is equal to Nd, right? We've discussed this one multiple times, where we assume 100% ionization of the dopant atoms in the lattice. So donor atoms, therefore is N, therefore is N0. The population of free electrons increases. Okay, population of free electrons increases because we add the electrons into the system by the dopant atoms from group 15, like phosphorus, arsenic, antimony, right, which has a 1 extra electron for every dopant atom incorporated into the lattice. So N0 is now given by Nd and also equals to this equation. And let's revisit the what you call the Fermi-Dirac distribution function and density of free electrons and density of state as well. So if you notice last time in our intrinsic calculation, the Fermi level here, Fermi level for this intrinsic silicon stays in the middle of the band gap, right? So this is the band H for conduction band. This is the band H for the valence band, and EF is equal to Eg over 2. Okay, Eg over 2 for this case, right? And if you translate that into Fermi-Dirac distribution function, you can draw this energy state at the same level of the middle of the forbidden gap for density of states on the right. So let's compare this to the case of N-type, right, where now you have lots more new electrons incorporated into the lattice, and now the electrons become your majority carriers. So do we have any majority carriers in the previous case? Tak ada kan? Dia N sama N and P sama dekat intrinsic. So in this case we have electron as the majority. So that is evident by the shaded areas, which in the N-type, which is a lot larger than this one. It's very small blue region, minority. So electrons are the majority carriers and holes are minority carriers. And note that your EF has now shifted. Okay, tadi intrinsic EF stays right in the middle. It was here last time for intrinsic. So it was here. So that's about Eg over 2 as well. Band gap divided by 2. So now your EF has shifted due to the N-type doping. Okay, we've discussed this one last time. What happens to the EF when we dope our semiconductor to N-type, going up, or P-type going down, right? So, and then this EF is also near to the conduction band H. Okay, again, the electrons and holes are in thermal equilibrium with the lattice, same temperature, and we still can use this equation, N naught P naught equals to Ni squared, and given by the middle equation, the simplified one. So in which you can use the thermal law of mass action equation for thermal equilibrium. So note that here, naught here denotes thermal equilibrium, not P naught or N naught. Right, the moment it's no longer under thermal equilibrium, you can no longer use naught. So it's no more N naught or P naught, it's just N, or N under certain conditions subscript, or P under certain conditions subscript. But you cannot use naught anymore because it is no longer thermal equilibrium. So that's N type. So how about P type? On the other hand, it's just the opposite of N type, where in this case, for P type, we can approximate the P naught to be equal to Na, acceptor impurity concentration, or acceptor dopant concentration, if you like, right? So note that the position of the Fermi level has now shifted downward, okay, near to conduction band H. Okay, and in this case, holes have become the majority carriers. You can tell by the shaded region, which is larger than the top one, N type, which is very, very small now. Minority carriers, okay? So EF is also shifted downwards near to the valence band H, okay? So due to the presence of more holes dope into the silicon. For Na equals to 1016, calculate the Fermi energy. Well, we've done this one last time. So you can use this equation, and you can also use this equation depending on the condition given. But bottom line, we know that P is equal to Na, and therefore N naught as the minority can be calculated by dividing Ni squared to Na, right? So let's recap. If your Na is equal to 1016, what's the value of your P naught? Anyone? Na is 1016. So what's the value of P naught? Same. What do you mean by same? Okay, P naught, right? Yes, exactly same. Okay, how about N naught? Okay, same value as Na. Yes, correct, because P is equal to Na. P naught is equal to Na. So how about N naught? What's the value of N naught? Berapa? Anyone? Shafika Azmi? What's your N naught value? You can write it down. So majority is 10 to the 16. So this is silicon. Let's assume this is silicon. How about your N naught? Yeah, 10 to the 4, right? 10 to the 4. Okay. Because 10 to the 20 divided by 10 to the 16. Yeah, 10 to the 4. So you can now compare the majority carriers and minority carriers. So, so it's proportional to the size of the shaded area. Okay, 1016 against 10 to the 4 is very, very small. So now it's clear. So intrinsic, the shaded region of N and P are equal. If you do it to N type, you're going to have like a lot larger shaded area for N type in comparison to P type. and for p-type, you're going to have a lot larger area of p-type for holes in comparison to n-type. Okay, and note the change of the Fermi level as well. Okay, Fermi level was right in the middle for intrinsic condition. Intrinsic condition, it stays right in the middle. If you do it to n-type, it's going to move up close to the conduction band edge. If you do it to p-type, it's going to move down right to the near to the valence band edge. Okay, that's very, very clear. We've repeated multiple times. Now let's look at the concepts of generations and recombination. So at thermal equilibrium, the net generation and recombination of charge carriers is 0. Okay, so that means in thermal equilibrium, we're going to have the same rate of generation and recombination, or R is equal to G. Okay, R equals to G. Thermal equilibrium condition. Ataupun G equals to R, sama. Generation equals to recombination. So the net is 0, which means R minus G will be equals to 0. So what is the number of carriers generated will be equal to number of carriers recombined. Okay, generated here means, okay, let me put it clearly. Generated here means number of electrons in the valence band excited into conduction band or going up. Okay, remember last time when we talked about transition number 1 and 2, when we discussed about direct semiconductor and indirect semiconductor. So transition number 1 is generation, and transition number 2 is recombination. Okay, so we discussed this one indirectly last time. So generation is when your valence band electrons excited into conduction band, and recombination is the opposite way, when it drops back to the valence band to recombine with hole, and we're going to have annihilation. So the recombination rate is proportional to the carrier populations and equal to generation rate as well. So R is equal to G and also equals to B N naught P naught. Beta times N naught P naught. This is how you calculate the rate, okay? The constant there, right? For good quality intrinsic silicon, the thermal generation rate is typically around 10 to the 13 per centimeter cube per second, and can vary over many orders of magnitude up to 1 times 10 to 17 per centimeter cube per second for poor quality crystalline. So the good one is, okay, generation rate. Okay, notice the difference. So now we have learned about thermal equilibrium condition in intrinsic, in n-type, and also in p-type. So sekarang, when you have learned about thermal equilibrium, now you already know, or you have to know already by now, what's the value of your N naught and what's your value of P naught. So depending on either you're working on intrinsic or N-type or P-type semiconductors. Now, in this part, in excess carriers, we're going to see introduction of new carriers into the system. So it was like thermal equilibrium and everything is settled, and suddenly somebody else coming in, right? So say if you rent a room, then you rent with your other 2 roommates, for example. So you're gonna have like 3 in one room, and you have rented the room for like 1 year, and suddenly there are 2 more new students coming into the room to join you, right? To make the space more occupied. Okay, so this is about excess carriers, introduction of new carriers into the system. So in this case, it can be silicon, it can be into the device. So in excess of thermal equilibrium condition. So you're going to have more than the values of thermal equilibrium carriers. Okay. So in order to generate excess carriers, there are a couple of methods available that we can use. So we can use, for example, optical excitation. Okay, what it means by optical excitation is you can just take your silicon, for example, if you're referring to silicon as your host or as your system, and then illuminate your silicon with light. Okay, illuminate with light. So then under certain conditions, we're gonna discuss later on what are those conditions. You will generate excess carriers. Okay, you'll generate excess carriers. But not all conditions can generate excess carriers, even though you illuminate the light onto the silicon. Okay, so you need to then understand what are those conditions. Other than that, excess carriers can also be generated by electron bombardment. So for example, you have an electron gun, and then you put your silicon in front of electron gun, for example, and then you shoot the electron beam right onto the silicon in order to trigger some collision that will knock out the valence electrons from the silicon lattice out to the conduction band for conduction. So in this condition, excess carriers are also generated. Okay. So remember when I say excess carriers, it's about transition number 1. Okay. So this is your EV, this is your EC. So you want to knock out these valence electrons into the conduction band for conduction. So the moment they are generated, the moment they are excited into the conduction band, they are now called excess carriers. Excess carriers. Oops. Excess carriers, huh? Okay. Electron bombardment. Okay, the third one we have covered already last time. So you can also generate excess carriers by doping, or we also call it carrier injection. Okay. So we have discussed just now that, so hold on, let me see. So we discussed just now, say if this is your original condition, intrinsic, so then if you turn into the next page, you are already generating excess carriers. So look at the shaded regions now, they are equal in intrinsic condition, but the moment you dope it to n-type, you're going to change this. And these n-type, the new areas in the conduction band, the larger area of the n-type, is now called excess carriers, okay, due to the excess carriers, which is contributed by doping. In this case, the third way of doing it, right? So let's get to the solar cell later on when we talk about device, but that's how it works. For example, if you talk about solar cell, then what you have to do is you have to put the solar cells or solar panels under the sunlight, and what we are actually getting is electrical energy out of it, right? So we pump in, we illuminate photons or sunlight, photons, and then what we get out is IV curve or electricity or electrical energy, right? It's going to be in that shape. We won't learn later on, don't worry yet. That's the IV characteristic of a solar cell under a typical operating condition. Okay. Then, in order to enable this, we're going to have p-n junction that we're going to cover later on after this topic. Okay, p-n junction. How do we join p material, which has holes as the majority carriers or excess carriers, and then electrons on the other side, which has n-type, which has electrons as the majority carriers or excess carriers combined together, and to enable a photovoltaic effect, as in solar cell. So when I talk about solar cell, then you are actually referring to optical excitation in order to produce excess carriers. So what actually happens when we generate excess carriers in n-type silicon, for example? Okay, so let's look at it now. An additional carrier density or excess carrier density or new carrier density of your electrons or new carrier density of holes, for example, depending on n-type or p-type, can be generated by external effects such as light or carrier injection. So in this case, if you talk about light, for example, or carrier injection, or by doping, the condition that we discussed last time, where NP is equal to Ni squared, will be turned into NP more than Ni squared. Okay, the product of N times P will now be more than Ni squared. It's no longer equals to Ni squared. This is away from thermal equilibrium, but still in steady state. So this is not under thermal equilibrium, But if you shine the light constantly, it's going to be under steady state condition, right? So that's why understanding the concepts of thermal equilibrium and steady state is important, right? So what happens now? Okay, if you look at the n-type, so now we're going to look at the new density of electrons and holes. So let's say, okay, let's go to the equation first, then I'm going to give you some example for it to make sense. So N naught here, what is N naught? And what is his P naught? What is this N naught and P naught that we discussed before? Why do we call it naught? Right, thermal equilibrium condition, right? So you start off, okay, before you introduce excess carriers, this is what you have, N naught. And this is what you have, P naught, before you shine the light to the silicon. So in this case, let's assume we shine the light as one method to generate excess carrier, the first one, optical excitation, right? So you start off with N naught and P naught, and that's it. So your shaded region should be equal to each other, the N and P, under equilibrium condition. Now, what we're doing is we're shining the light, and we are now introducing delta N and delta P into the system. Okay, so delta N and delta P refer to excess carriers generated by illumination of light to the silicon. And note that when you generate delta N and delta P, should they be equal to each other, or one should be more than each other? Delta N and delta P. What do you think? When you generate new electrons, are you generating the same amount of new holes as well, or not? In the case of optical excitation, are we generating the same amount of delta P and delta N, or okay, same? Kenapa same? Why is it same, Haziq? Kenapa sama? Remember last time when we talked about generating carriers, what is required in order for you to generate? Yes, conservation, but physically what has to happen before you can have your free electrons? What has to happen first into your silicon before you can have your delta N or delta P? Anyone? I think we learned last time, like 2-3 weeks back. What has to happen? Yes, thermal excitation. So that will give you the equals amount of delta N and delta P. In this case, it's not thermal excitation, Faris. It's by the light. It's not by the heat. It's not new. It's not at higher temperature. So let's assume the same temperature, but now you shine the light to silicon. So in order for you to have delta N, new carriers, new excess electrons, what need to happen physically in the silicon? So that we understand. For you to have free electrons, you need to break a bond, right? Isn't it? Don't you have to break a bond? Right, okay. So don't you have to break a bond? When you break a bond, what do you have? You're going to have electron hole pair, right? Electron hole pair together. They were together. Now they are broken and separated. One goes up to conduction band, one stays in the valence band, right? So they are actually in pair. So the moment you have one new free electrons, yeah, every electron after excited one hole also exists. Yes, exactly, good. So they were in pair, they were together before that, right? Before you break by the optical excitation. We will understand later on, we will learn on under what condition they can be broken. Sebab it's not under all conditions though. They need to satisfy certain criteria before it can happen. So let's assume it happens. You need to break a bond in order for you to have delta N. So the moment you break a bond, you're going to have delta P at the same time. So one electron generated means one hole left behind. So then you're going to have the very same amount of delta N and delta P introduced into the system. Okay, so now you have to recall again, you started off with N naught and P naught as your thermal equilibrium. Now you shine the light, shining the light introducing delta N and delta P, and delta N is equal to delta P because in order to get delta N, you need to break a bond, right? Because they were together, they were in pair. Breaking a bond means one electron excited into conduction band, leaving one hole behind in the valence band. So that's why delta N equals to delta P. Right, so let's look at this equation again. Therefore, your new N, so N here and P here will be your new density of your electrons and holes respectively, right? So your new concentration of electrons and new concentration of holes. You can use either concentration or density, same thing. Don't worry about it, right? So delta N, your new N, under excess carrier condition, will be equals to your N naught, your original number, plus your new number, right? Original number, which is N naught, plus your new number, which is delta N. Okay, so don't worry about the approximation to ND yet. So the same goes to P. Your new density of holes is equal to what you have originally P naught plus what you have as your new excess carriers, delta P. So P naught plus delta P. All right, so let's take a number and make sense of this equation. Assuming your, okay, let's assume this is your N-type. So this is N-type. Okay, we were discussing an N-type anyway. So let's assume your ND equals to 10, 17. Okay, so your ND is equal to N to 17. So what is the value of N naught in this case? Okay, apa value N naught? If your ND is 10, 17. Anyone? Baru discuss tadi kan? If your ND is 1017, then your N naught is of course 1017, right? 1017. Okay, therefore your P naught is berapa? Thermal equilibrium condition 10 to the 3, right? 10 to the 3. Okay, 10 to the 3. So N naught is 1017 and P naught is equals to 10 to the 3. Okay, let's assume if you shine the light, you are generating delta N and delta P of 10 to the 12, for example. Katalah you generate this much of new excess carriers, 10 to the 12. Okay, assuming. So let's put this into equation. N equals to delta N plus N naught. So that means delta N is what? Delta N is 10 to the 12 plus N naught, berapa? 10 to the 17. So what do you get? 10 to the 12 plus 10 to the 17. What do we get? Look at the order of magnitudes there. You can tell already, right away. 10 to the 12 plus 1017 is going to be equal to 1017, right? Okay, because the 10 to the 12 will be negligible to 1017. It's like 5 orders of magnitude smaller. So your result will be 10 to the 17. So that's how you get your value to be approximately equal to ND. Okay. So let's put it for P-type now. So now your value of N is now 10 to the 17. What if we try for P-type? So your P will then be equal to, what is delta P? It's 10 to the 12 plus P naught. What is P naught? 10 to the 3. So what do you get? 10 to the 12 plus 10 to the 3. 10 to the 12, right? 10 to the 12. And that is equal to delta P, right? Because 10 to the 12 is way bigger than the minority carrier concentration. So this, if you look at this, we can see that if sebab dia ada condition, there will be other condition as well. If your delta N or delta P is somewhere smaller than your original majority carrier concentration, it's not going to change the majority carrier concentration, but it only changes the minority carrier concentration. Okay, if your delta N is somewhere here, 10 to the 12. So it's not going to change your ND because your N will still be equal to the original value anyway. Okay, because delta N doesn't change anything to the majority carriers, but it's going to change the minority carriers only. P is no longer 10 to the 3 as given by P naught, but now equals to P 10 to the 10 to the 12. So if you can summarize this, now your N is still equal to ND, but your P is now equal to delta P. Okay. So majority carriers are not affected by excess carriers. However, minority carriers are affected by excess carriers. When the excess carriers have orders of magnitude lower than the majority carriers. Okay, this is called low level injection. Low level injection, LLI. What if? What if yang satu lagi tu apa? If it's not low, then what? High, right? High is more complicated than this. Okay, there are conditions when the delta P could be 1016, and 1016 is definitely affecting 1017 by 1 decimal place, and of course it's going to affect the minority carriers significantly, right? So the optical generation will create extra or excess charge carriers, delta N and delta P in the semiconductor. Why is this case thermal? Why is this case away from thermal equilibrium? Well, you can tell by the value of the new N and new P. So is it away or not from thermal equilibrium? Right. So we're gonna continue on carrier injection tomorrow, which is briefly what we've discussed just now. So we can see this example. Sama aja yang saya bagi tadi, except the value of ND is no longer 1017, it's 1015, but if you plus 10 to the 12, it's going to be equal to the original condition as well. Or if this one is ND, then it's going to be approximately equal to ND. And if you do the same thing to the minority carrier is going to be changed and equals to delta P. Okay, so majority carriers are not going to change, and minority carriers are going to change. It's called low level injection. Okay, we'll continue tomorrow on this. So as of now, is it okay? Is it clear in terms of steady state, thermal equilibrium, intrinsic condition, N-type condition, P-type condition, and then how does the excess carriers change? The majority carrier, in this case, no, and a minority carriers, in this case, yes. Okay, so this is the equation that you have to always remember. Okay, and the new N is given by your delta N naught, the original thermal equilibrium concentration, plus the new excess carriers, and delta N and delta P are the excess carriers, and they are equal to each other because to be able to have delta N and delta P, you need to break a bond. Breaking a bond means having one electron excited into the conduction band and at the same time having one hole left behind in the valence band. Right? So okay, all good so far. We're gonna no tomorrow, right? Because tomorrow is Friday already. So I'll see you next week then. We're gonna continue to carrier injection and the rest. Okay? Ada soalan? Any question so far? I'm gonna give you your assignment 1 tomorrow, and you're gonna be given 2 weeks to finish. So it's gonna be 2 more Fridays. Okay, 2 more Fridays, 5 p.m. You're gonna need to submit on e-learn. Okay, in PDF. I'm gonna give you the instructions anyway, but just we call heads up for you before you receive the assignment 1. Okay, that's all eh? Right then, I'll see you next week, inshallah. Bye bye. Take care. Assalamualaikum.